Yeah, so I will record this session just in case if you want to go back to any items that we didn't discuss. And also for the people that who are not on the Zoom with us right now. Okay, let's copy the seminar name. All right, let's get it started. We have 11 in the room. Um, Okay, so let me introduce myself very quick. So my name is Omar Nofal. I'm a PhD candidate at Colorado State University. My research spans in multiple fields, like I have been working over the last 3 years on flood risk analysis and flood mitigation and flood vulnerability. And currently, I have been working over the last year on hurricane damage assessment in terms of developing multi-hazard vulnerability approach. And also, I plan to work on tsunamis and earthquake in the future, maybe next year. I'm doing my PhD within the Center of Risk-Based Community Resilience Planning Center at Colorado State University. And today's topic that we are going to talk about the how I developed high resolution flood risk model. So the motivation behind this work is that uh, most all of the current flood risk analysis approach are focused on high resolution flood hazard maps with less focus on the exposure and vulnerability component of the risk. So risk consists of hazard, exposure, and vulnerability. And if we need high resolution models, we need to develop high resolution model for all of them, hazard, exposure, and vulnerability. Most of the current flood damage assessment methods are based on deterministic stage damage functions, which lacks uncertainty propagation in the damage models. So in my research, we developed a high fidelity flood risk model using high resolution model for the flood hazard component and the flood exposure component and the flood vulnerability component. The analysis resolution used in this model allow for flood mitigation analysis at the component level and building level and community level. So we expand these components to have them be applied on a high resolution flood risk model. So basically our models start with multiple analyses on the digital elevation map of the study area to account for the basin characteristics, including the river's length and slope, the basin's characteristics, and the longest flow path. Afterwards, we developed hydrologic models using the multiple methods like the loss and transfer method, the base flow method, and the routing method. This was done by using the rainfall data along with the land use and soil to perform detailed hydrologic analysis. So what we get from the hydrologic analysis is the hydrograph, which is the which give us the timeline of the discharge over the flooding event. Then we use this hydrograph as a boundary condition for hydrodynamic analysis to account for the flood inundation map. So we were able to get the flood inundation map in terms of riverine flooding, but we also can get the flood velocity and flood duration map. Afterwards, we developed a detailed exposure model of the community This includes detailed information about each building within the community so we can have a high resolution community model. Afterwards, for each building within the community, we developed a fragility function for a portfolio of building archetypes that enables us to account for the amount of damage and losses at each flood depth for each building. This allows us to have a high resolution flood risk model. So let's now go and see what is the data analysis included in this research. So developing high resolution models for flood risk and mitigation were hampered by the data scarcity because there isn't much data about the buildings, even the flood itself, or even the buildings themselves. So the different levels of resolutions available in the literature ranging from parcel level, census block level, or census tract level, or even the hydrologists are usually use land use as a vulnerability a vulnerability level for their analysis. So modeling either the community level or building level flood risk requires several levels of data analysis if we need to come up with a high resolution model. So in my research, we handled multi-level data. This includes community-level data, such as the digital elevation map, the land use map, and soil map. We also used many building-level data, including the building value, location, archetype, foundation type, vertical floor elevation, building construction material, occupancy, along with many different information about the building. Even the components within the buildings, including furniture, appliances, structural and non-structural components, we were able to have the components as statistical parameters in terms of the damaging elevation, the damaging duration, the replacement cost, all of these information we have about the component within the building. Afterwards, we were able to get we were able to do data analysis for the community and building and components within the buildings. So this enables us to have component level fragility functions, which accounts for the failure probability for each component within the building. Then we use these components failure functions, which we call it fragility function, to develop a building level fragility function that accounts for exceedance probability of a prescribed damage states for the building. Like we can say that this the building got like damage state 1, which is minor damage or low damage, or damage state 2, which is medium damage state 3, which is extensive, or damage state 4 is a complete damage. Afterwards, we propagate our method to be used at the community level so we can account for the whole damage for the community, any community exactly. So this resolution enables us to do mitigation analysis at different levels. This includes a component level, such as what will happen if the building has non-return valve, or they reroute the ductwork during re-innovating their buildings, or using flood resilient material in the construction, or increasing the components elevation like their valuable items, including electronics and appliances. We also investigated different building level mitigation measures, such as using a water pump to pump out the water from your building to outside your building, using a buyout policy, or using a flood barrier system, or increasing the building elevation. We also were able, which was easy, we were able to investigate community level mitigation measures. This includes building levees, flood walls, floodgates, or even retention systems. So this shows like a brief description of what the data analysis that we handled in our research. So we applied our method we need to apply this method at the community level. So we used Lumberton, North Carolina, to be the case study for this method. However, we applied this method for multiple communities, including Santa Clara County, California, Waveland, Mississippi, and I and we done like something similar for the whole state of North Carolina. Lumberton City is a small city within Robeson County in North Carolina. So here it shows the physical boundary of Lumberton, North Carolina, and these dots represents the buildings within Lumberton. So the green dots shows this is a residential building. However, the other colors represent the commercial buildings and social institutions within Lumberton. This shows the topography of Lumberton. So here's the magenta color shows the physical boundary, and the blue color here shows the main streams that deliver the water to the study area. So we have Lumber River on the west side of Lumberton, comes from here, and we have on the north side, we have Red Spring Creek, which is a small creek that also delivers the water to the study area. The west side of Lumberton is protected by the embankment of the Highway 95, this highway, along with a levee, the one in the red color here, that dams Lumber River from this location and doesn't allow the water to jump in or and swell on this location of the city. However, there is a gap in the intersection here. So the levee in this location, and here there's an intersection underpass uh, between the I-95 highway and there's a railroad down there. This gap led the water to go inside Lumberton for both Hurricane Florence and Hurricane Matthew, which will show in just a few minutes in our simulations. We used a hazard scenario. So the flooding event after Hurricane Matthew 2016 were used as a flooding event for Lumberton, North Carolina. So Hurricane Matthew started as a Category 5 storm in the Caribbean and ended up with Category 1 storm on the east coast of the U.S. and North Carolina specifically. So 10 inches of rain fell from Hurricane Matthew on Lumberton, North Carolina, which rose Lumber River 24 feet high, which was higher than ever recorded. This water kept the Fell Lumber River and its tributaries to swell and overflow onto the adjacent community of Lumberton. So this is one of the pictures from the Wall Street Journal that shows how is the state of flooding in one of the neighborhoods in Lumberton. And this figure actually, the above one here is from NOAA that shows the precipitation map, and here actually, which is the maximum precipitation at Lumberton in the purple color, that got 10 inches of rain here on that scale. First, we developed a hydrologic analysis model using the digital elevation of the study area along with the rainfall information collected from NOAA. And we were able to delineate the study area. And here it shows the main catchment within Lumberton, North Carolina. So there are two main streams, one of them here in Maxton and the other in Red Springs. And here is the downstream in Lumberton. So this is the sources of water. And we have two USGS gauges that provide the state of water flow at Maxton and at Lumberton, but there wasn't a one for Red Springs. So we were able to validate the calculated discharge at these two locations using the gauges at these streams. However, this ungauged streams, we use the calculated discharge for the hydrodynamic analysis. So here it shows one of our simulations for the for Lumberton. Here we use the hydrographs that we calculated as a boundary condition here at Maxton and here at Red Springs, and the two streams get together before they enter in Lumberton. And as we can see that the highway worked very well in retaining the water and same as the levee. However, this gap was responsible of most all of the water that gets inside into the city. So this video shows the one of the Florence drone footage that shows how the water was able to get into the city. And here's how it shows like gap, and here's the underpass. Actually, this is the railroad, and this is the interstate. And this is actually one of our simulations that we have for the flooding event after Hurricane Matthew. So moving from the hazard modeling to modeling the community. So we needed to model every building within the community. So we needed detailed data about each building within the community. We were able to get some of them from the North Carolina spatial data download. However, we missed many data that we needed to do our analysis. So we used Google Street Map View to navigate the buildings within Lumberton, which are more than 20,000 buildings. We navigated them building by building to collect multiple informations, including building material, number of stories, occupancy, use, archetype, versus floor elevation, along with many other data. Afterwards, spatial analysis of the collected building data was conducted in a GIS environment. So this is some of the buildings, and this is the shapefile of some of the buildings and how did we handle the data in terms of the shapefiles. In ArcGIS, here it shows the X, Y coordinate of each building, and this is some of the data that we collected, including number of stories, foundation type, occupancy, building archetype, building area, qualitative assessment. And this is some of the data that was provided by HAZIS, included the HAZIS occupancy and HAZIS ID. Afterwards, we needed to develop a high resolution model for the community that we could handle in our vulnerability model. So we developed a portfolio of 15 building archetype. This archetype is supposed to model most all of the building occupancies within the community. So these 15 archetypes in this 15 building archetypes include 4 residential building, 4 commercial building, school, hospital, a church, office building, warehouse, industrial building. So we try to cover as much occupancy as we can. Afterwards, these archetypes was assigned to each building within Lumberton. So the scholar coded buildings are based on our 15 building archetype. So here's it shows how we mapped our building archetype. So this is one of the neighborhoods in Lumberton, and this is two of our archetypes, and this is the mapped community. So right now we are moving from a community that has a lot of buildings to a mapped community that we can handle in our damage analysis. Yeah, so here's it. It shows when we overlay the hazard map over the buildings in Lumberton. So here it shows the buildings that only in the floodplain. So we excluded any building outside the floodplain. So we have like 24,000 buildings in the floodplain, and they are color coded based on their archetypes. So for example, the green color, which is building archetype 2, we have 1,500 building designated as archetype 2, and this table shows us that archetype 2 is a 1-story residential building on a slab on grade foundation. Similarly, we have 11 building and the orange color designated as archetype 14, which is an office building. And similarly, we can do it for all the different building archetypes. Afterwards, we needed to develop vulnerability model for each one of these archetypes. So we divided each building into components, and we investigated the flood susceptibility of each one of these components. Afterwards, the resulting component failure metrics is used to develop a fragility and loss function for all the building. So here's it shows how the building was divided into components and the distribution of the damaging depths and the damaging duration. And then we develop components, fragility, surfaces, curves and surfaces, because we did a single variable flood damage analysis and multivariate flood damage analysis. The single variable includes the impact of flood depths only, and the multivariate include the impact of flood depths and flood duration. So we used Monte Carlo simulations to simulate the component resistance in terms of the flood depth resistant and the flood duration resistant. And afterwards, we were able to develop a fragility curve, which gives us the failure probability of each component, and a fragility surface that includes the failure probability of each component given the flood depth and flood duration. Afterwards, we were able to develop building level, not a component level. So we moved right now from the component to building. So we developed also a fragility curves and fragility surface for the whole buildings using a set of damage states. So to show you how did we calculate the failure probabilities of the components, so I'll give two examples of the EC unit and one of the electrical receptacles within the building. So the EC unit there's a high uncertainty in the elevation of the EC unit. It could be rested on the ground or it could be elevated by 2 foot as shown in this figure. So we developed a truncated normal distribution that propagate uncertainty of the location of the EC unit between two upper and lower bound of the elevation. So the lower bound of the elevation is the ground because I will not dig in the ground and put the EC unit, and the upper elevation is based on field studies, what we saw from actually what the buildings did in terms of elevating their EC units. However, the mean elevation of the EC unit is usually at the elevation of the first floor elevation. And similarly, we did this for the electrical receptacles and the TVs. Like the TVs could be on a table that is 2 feet from the ground, or could be mounted on the wall at like 4 foot or 5 foot from the ground. So we did this for all the components. This is the equations that we use. So this the equation give us the failure probability of each component at intensity measure, like say flood depth equal to 1 meter, and this calculates the number of fails over the total number of simulation to calculate the failure probability at each intensity measure. And similarly, we calculate the replacement cost or the loss for the component by multiplying its probability of failure by a vector of randomly simulated replacement cost to get a 1,000 simulation of the replacement cost of the component. And we summed the replacement cost for each one of these components. So for archetype F1, we have 65 component. If we sum the 1,000 simulation replacement cost of each one of these component, we will get the total replacement cost of the building. And the total replacement cost of the building is a 1,000 simulation. And if we take the mean of the simulation, we will get the mean replacement cost. And we also were able to get the standard deviation of the replacement cost of the components of the whole building. Sorry. And moving from components, we needed to develop the fragility for the whole building. So we started by define some damage state for the buildings that shows like this building is damage state 0, which means that the flooding is outside the building, but the building is safe. The water that wasn't able to get inside, so it's damage state 0. Damage state 1, like you have 2 inches of water inside the building, which make a carpet damage or flooring damage, base pour damage. And this is damage state 2 when the water makes like 2 feet inside the building. So you will have most all of the appliances are damaged, cabinets damaged, full damage to the flooring. And this is damage state 3 when the water reaches like 5 foot or 6 foot from the ground, which destroy most all of the component within the building. Damage state 4 is the stage when you got all the interior content and non-structural components damage, and also you will have a structural damage. However, right now in the center, we are trying to reduce this damage state from 5 to 3. So we plan to merge damage state 0 and damage state 1 into damage state 2. So we will only have medium, extensive, and complete damage. And this table shows the functionality description of each one of these damage states. So damage state 0 means the building is operational, but damage state 1 is limited occupancy. You can live there, you can stay there and dry the building, but it's limited. Like somebody will leave and until the building get cleaned. However, damage state 2 is restricted occupancy, and 3 is restricted use, and 4 is restricted entry because it's unsafe. And this is the damage ratio associated with each one of these damage state. Like if I have damage state 1, so I expect that the building will lose from 3% to 15% of its of the in terms of losses as a percentage of the market value of the building. When I say market value, I mean the value of the structure and the interior content. This is ranges, but we have calculated them exactly for each one of the archetypes that we have. So we have detailed component replacement cost analysis for each one of the 15 buildings archetypes that we developed. Yeah, so shows us the components within the buildings. This is one of the Excel sheets. So for archetype 1, actually, so we have 65 components. I have the minimum and maximum elevation of each component, and then we get the mean and standard deviation, description of the elevation of the component, and also duration, resistance. And also this is the cost analysis of the component. So we did like detailed unit price and multiply each unit price by the total quantity of the components. If I'm like doing like carpets, so I have the price of each foot square of the carpet, and I have the total area of the carpet. So we did detailed cost analysis, and we grouped these components based on their damage state. So we have the crawl space isolation and the flooring insulation. In damage state 0, we have the HVAC and the EC unit, heating unit. In damage state 1, we have the appliances, refrigerator, stove, dryer, washer, cabinets, lower cabinets, TVs. In damage state 2, and damage state 3 includes counter items, upper cabinets, electrical receptacles. And damage state 4 includes the wood framing, the roof sheathing, the roof framing, foundation. So we grouped these components based on their how they are associated with each damage state. Afterwards, we needed to develop a fragility curves for the whole building. So we need to know the exceedance probability of each damage state for the building. So we have the failure probability of each component associated with each damage state. So we weighted these failure probabilities based on the replacement cost of each component with respect to the replacement cost of the whole damage state. So these four fragility curves is for the 5 components that construct damage state 4, which is a structure damage. So the CN1 is the wood framing fragility. The green is the roof sheathing, roof trusses, foundation, and flooring. So these 4 finally give us one curve, which is the dotted one here, which is the exceedance probability of damage state 4, because these 4 components represent damage state 4. Afterwards, so to make our analysis fast and to be able to use them in many platforms, we log normal fitted this fragility using log normal function. So the solid lines here is the log normal fitted fragility functions. And this is the equation of the log normal fitting. So we were able to get the log normal parameters, including the mean and the logarithmic mean and the logarithmic standard deviation. And we applied this method to the 15 building archetype, and this is one of the example building archetypes that we have. It's a 1-story residential building on a crawl space foundation, and this is the plans in the 3D view for all the building. And this is the component fragility analysis. Here it shows the list of the components that we have here in the Excel sheet, 65 component, and this is the 65 fragility function for each one of these components. And this is some of the loss functions along with one standard deviation in their replacement costs. So this is 6 components only, so I can able to plot them clear. And I have them legend. I have the legend for them here over there. And uh, we used these fragilities for the components to develop this whole building level fragility curve. So we have damage state 0, 1, 2, and 3, and 4. So we basically have our flood depths equal to 2 meter. We calculate the exceedance probability of damage state 3, damage state 2, damage state 1, and damage state 0. Also, we developed 2 ways for calculating the loss associated with each flood depth. So one of the flood loss functions that we developed is based actually on the water. When the water goes up, we accounts for what components that got damaged, and this was done using Monte Carlo simulation. So at each flood depth, let's assume that we have flood depths equal to 2. If I take a section here, I will get 1,000 point, which represent 1,000 simulation of the replacement cost of the component of the whole building. And this replacement cost of the whole building actually is the summation of all the damage component at this flood depth. And we also calculated another flood depth, which is the blue curve here. Actually, this flood loss curve is calculated based on this fragility function. So what we did, we use this equation. We calculate the probability of being in each damage state and multiplied by the replacement cost of this damage state, and sum all of these for the 5 damage state starting from damage state 0 to damage state 4. This gives us to the blue curve here, which is like very close to the black curve that is based on bottom to top flood damage analysis. And the red curve here shows the Hazes stage damage function, which shows like a great match with our loss analysis up to flood depths 4 meter. But after flood depths of 4 meter, Hazes stage damage function didn't increase more than 80%. However, our function can goes to 100% of damage. This is because like Hazes assume if the building was fully submerged with water, the structure will be there and it can be used. But our assumption, if the building is fully submerged with water for a certain duration, we will be losing the structure due to many structure consequences, like foundation scour, long duration affect the wood itself and its connection, and something similar to that. And this is the multivariate loss functions that we have. So the other curves is only accounts for the flood depths. This loss surface account for the flood depths and flood duration. So we can calculate the failure probability of each component given the flood depths and flood duration. And similarly, we can do for the loss. And also we can do this for the whole building. At each flood depth and each flood duration, we can calculate the exceedance probability of each damage state. And also we can calculate the percentage of the loss. Like for example, if I have the flood duration equal to 60 hours, and I can get like a curve over there that calculates the flood loss at each flood depth. And here we project the Hazes stage damage function in red, and this is our flood loss function. The black one is based on the component, and the blue one is based on the fragility. We applied this method for all the building archetype. This curve is only for archetype F1. So we applied this actually for this is a 2-story residential building on a crawl space foundation. And we also applied it for a gas station with a convenience store, super shopping center like Walmart in US, strip malls and multi-business building, office building, school. We have a 1-story and 2-story school, hospital, community center. So we did it, this is actually some of the archetypes, but we did it for all the 15 building archetype. Afterwards, we overlay the hazard map over the community model to identify the exposed buildings. So here's it shows the map for each exposed building. And we know the building archetype of each one of these buildings here. I have them color coded based on their archetype from 1 to 15. And I have the fragility curves that calculates the flood vulnerability for each one of these archetype. Then we developed an algorithms that reads the hazard and exposure and vulnerability and then go building by building from 1 to n and calculate the exceedance probability of each damage state from 0 up to 4, and then calculates the probability of being in each damage state, and then assign a damage state for each building based on the maximum probability. And also we calculate the loss associated with each building, and we did this for all the buildings. And here it shows the results that we have here. Here it shows the buildings color coded based on their damage state. So we have the building, the blue color coded buildings here has damage state 0, and the yellow buildings is damage state 2. We didn't got much building with damage state 4, just like maybe one here on the river. And we also calculated the loss as a percentage of the building total market value. So we have like the building in the blue has like from 0 to 3% loss, and the building in orange have 50 to 70% loss, these buildings. So this is a deterministic quantification of the damage. So we didn't lose our probabilistic analysis. So we have here in this table the number of buildings within a set of the exceedance probability range. So like here we have like 2,200 building have exceedance probability of damage state 1 of more than 80%. And we have 1,700 building with exceedance probability of damage state 2 of more than 80%. So we still have the probabilistic damage analysis, we didn't lose it. So let's move to the second stage of my research, which is the mitigation analysis. So we expanded our framework to include the different mitigation measures that could be done at building level. So here's in the flow chart, it shows what if we were able to use a barrier height with a height of HB. However, the barrier will not work properly if there is not a non-return valve in the sewer pipes. So we need to check if there is a non-return valve in the sewer pipes, if the flat walls are resistant, if actually there's a flat barrier or not, and what is the height of the flat barrier. Then this takes us to two analyses, flood fragility analysis and flood loss analysis. And when we get to the flood fragility analysis, it takes us to a multivariate and a single variable. The multivariate check the duration. The single variable doesn't check the duration. It takes the flood depths directly to do Monte Carlo simulations and calculate the component fragility and building fragility. Similarly is the flood loss analysis. So it takes us to multivariate, so it accounts for the duration, and single variable that goes directly to Monte Carlo simulation with the flood depths, and finally get the component loss and sum all the components from 1, 2 up to n, and finally calculate the total loss of the building. So here's it shows like how if a building actually use a flood barrier. This is this picture actually from one of the businesses in Lumberton, North Carolina. This is the business during the flooding event after Hurricane Matthew in 2016 without any barrier system, which we can see that the water were able to breach inside. However, here it shows the same building during Hurricane Florence were able to construct a flood barrier system. And this is one of the drone footage that shows how's the building look like. The water is out there and the building is fully protected. So to model this, we included this in our fragility function. So this, our fragility function and loss function without flood barrier. And if we have a flood barrier, assuming this flood barrier is 1 meter height, so if the flood depth is less than 1 meter, so we will have zero losses and no damage. However, if the flood exceeded the barrier height, we assume that this barrier will fail and all the water with full depths will breach inside the building, and we will have immediately a 50% of the building loss, and we will hit exactly on damage state 3 and damage state 2. Also, we investigated the impact of flood duration. So as we have a multivariate fragility function and loss function here, so if we were able to decrease the flood duration, this would affect but it depends on what the duration, how much duration will be decreased. Like if the building has already the building was 10 days flood duration and I reduce the duration to 8 days, I will not be able to save that much. But if it's 10 days and reduce the flood duration to 2 days, so I might be able to reduce the losses by like 30 or 20%. So here it shows the flood loss curves at each flood duration: 1 day, 2 days, 3 days. This could be done using a water pumps to decrease the flood duration just during the event. When you have some water breach in, you set up your pump and suck the water and put it outside your building. And we also investigated the impact of resilient construction. So what if the building has a non-return valve and have the ductwork in the attic, not in the crawl space, and the household have their appliances elevated, such as dryer, washer, fridge, and yeah, along with many other resilient construction materials. And this shows us actually the loss curves with mitigation measure and without mitigation, with mitigation measure in red color and the blue color without any mitigation. So if I have a building without elevated components, so the building will stick with this blue curve. And if I were able to use resilient materials and elevate the water sensitive component, the loss will be on this red curve. It seems like the loss reduction is not that big. It's like 10 or 8% of the building, which is the values of the components that you saved. If you were able to save your computer, your appliances, some of your furniture. So this is the amount of saving that you have. And this is the combination of decreasing flood duration and elevating the component. So if it's 1 day, so this is the two curves. If it's 2 days, this is the two curves. It seems like, as I said, it is not that much saving in losses. However, if we apply this at the community level, we can save millions of dollars. So this shows, this shows the state of losses for the buildings without any mitigation. The building is color coded based on the dollar amount of loss. So the red color building has losses from 0 up to 25,000. The yellow from 50 up to 100. And this, a close-up view on this location that shows the buildings in this neighborhood. So this without applying any mitigation measures. This shows if we applied 1 meter flood barriers, we can see that some of the buildings that has orange and yellow color are turned to be red, which means the losses were decreased from $50,000 to 0 or $25,000. And this one shows the impact of using a pump to decrease the flood duration to 1 day. It doesn't show that much saving losses such as using a 1 meter flood barrier. However, we can see that some of the blue buildings here are turned to be CN buildings, like from $200,000 to $100,000. So what is the impact if we use all of them? What if we used 1 meter flood barrier, decrease the flood duration to 1 day, and increase the elevation of the water sensitive components? We can say, we can see that most all of the buildings that has yellow and orange are tended to be red, which means a huge savings in the amount of losses. So this is for the building level flood loss mitigation, mitigation. So we applied flood barriers using pumps to decrease water duration or even elevate some of the water sensitive components. We also have some work that hasn't been published yet in building level flood mitigation measure. Oh, let me show you. Yeah, let me do this first. Um, so to be realistic about the building level mitigation measures, we can assume that all the buildings in the floodplain can apply these mitigation measures, or all the household have the chance to build a barrier or elevate their valuable components. It depends on many social and economic factors for the household, including the age, tenure, household income, along with many other social characteristics of the household. That's why we need to investigate and cover as much scenarios as we can. So we investigated multiple techniques like flood barriers only, pumps only, and a combination of these techniques, including using flood barriers and pumps or using three of them. And we also investigated using multiple scenarios, like what if the household was able to build a barrier of zero point 0.2 meter or 0.6 meter or zero point 0.8 meter? And what if they were able to make the flood duration 6 days or 2 days or 1 days, and also many combination of these scenarios? And what if, like, not all the household in the floodplains were able to do this mitigation measure, like 0% or 10%, 20%, 30% of the build of the household in the floodplain were able to apply these mitigation measures. And this shows us some of the results that we have. So here it shows the impact of the flood barrier. And this is the flood barrier scenario. Like here is zero point 0.2 meter, zero point 0.4, zero point 0.6, zero point 0.8, and 1 meter. And as we increase the barrier height, the amount of flood loss reduction, amount of flood loss get decreased. So we have more flood loss reduction. Uh, and each one of these curves shows the percentages of the household that respond and do mitigation, like 0% in the up curve, 50% up to 100%. Similarly, this is the impact of using pumps at different water duration, and this is different response ratios for the household, and this is the combination of the different mitigation measures like pumps and elevating components, flood barriers and elevating components, and this is flood barriers and pumps that shows what if we use the pumps and flood barriers at the same time, and we investigated the impact of the different response ratios of the households. So this is the end of the building level mitigation measures, and right now we will go to the community level mitigation measures. So we investigated the impact of we decrease the hazard itself or control the hazard. So what if we enhance the current levee system that is here, and we build a floodgate at the location that makes a breach inside the community, and we enhance the embankment of the roadway. So this works very well in tamming and controlling the water. As you can see, here is the floodgate works very well. It closed the water, but this simulation is one after many simulations, because when we did the floodgates alone, the water kept accumulating behind this gate, and the water made a reservoir action, and the water overtopped the embankment here and the levee system here. So we needed to enhance the levee system. And when we enhanced the levee system, the water breached from the embankment of the highway. So we needed to enhance the highway. So this is one of our mitigation scenarios that we have to control the hazard itself. And this shows the what if we were able to build a retention system here at this location to take the water, the excessive water from the river, and control it, and then release it as much as needed. And however, this system requires also enhancement to the current levee system at this location, but it didn't need any enhancement for the highway. So this is one of the two simulations that I have here, but we did a bunch of simulation. We investigated 28 scenarios, and the paper already submitted 4 months ago, and we are still waiting for the response from the journal. So finally, I would like to thank the Center for funding my research. So I would like to thank the NEST funded Center of Excellence for Risk-Based Community Resilience Planning. And also I would like to thank Colorado State University for supporting me during my research in terms of scholarships and many things and many supports during my research. And this is the end of my presentation. And let's uh, open, unmute, and see. Yeah, if anybody have questions. Oh, it takes me a long time actually. So you can unmute yourself if you have any question. Were you able to mute yourself? Just answer in the chat.
Uh, can you able to hear me?
Yeah, I can hear you.
Yeah. So my name is Subrajit Datta. I'm an assistant professor in the Department of Civil Engineering at NIT Silchar in India. It's a very interesting work that we're doing. Recently, I've also been working in this area of flood resilience for housing infrastructure systems. I'll be quite curious to know what kind of tools and softwares, etc., that you have used for your hazard analysis and also the vulnerability and exposure that you talked about.
Thank you. So do you have any question?
Yeah. Is it audible?
Yeah, I can hear you.
Hello.
Hi.
Yeah. So what I was asking. Yeah. I think I introduced myself earlier, but it's not audible. So shortly, my name is Subrajit Datta. I'm an assistant professor in NIT Silchar. So I've been working in this area also. It's a nice work that you have shown us. My question is, what kind of tools and simulation techniques that you use for the hazard analysis, the vulnerability, and the exposure conditions that you discussed about? So if you can just give some idea about it.
Yeah, sure. So most all of the data analysis was handled in ArcGIS. So the actually mainly the building level data was handled in ArcGIS. So we deal with shape files. The component level data was handled in Excel files, and we used a Revit to build a building information model for each archetype so we can identify the components. So we used Revit to build each archetype and then extract the components from Revit. And most all of the community level analyses was done on ArcGIS. Moving to the hydrologic model was done in HIC-HMS, which is one of the hydrologic tools provided by the Army Corps of Engineers in the U.S. The flood simulation, which is the hydrodynamic simulation, was done in HIC-HMS, which was also one of the hydrodynamic analysis platforms developed by the engineering department in Army Corps, and yeah, and we handled the building information. So this shapefile is from ArcGIS. Yeah, this is ArcGIS Pro. So we used like ArcGIS Pro sometimes, and yeah, and for the damage analysis, so it's like an algorithm. So we use Monte Carlo simulation. So we had to use a programming language. So I mainly use MATLAB to develop my fragility curves and handle the Monte Carlo simulation and the uncertainty analysis and the probabilistic damage analysis in terms of developing the fragility and the damage curves. So this is most all of the tools that I have here. And for the actually the two simulations that I showed in the last two slides here, this actually was done also in was done in HeckHMS. So this is most all of the tools. HeckHMS, sorry, this is HeckRAS, and we use HeckHMS for hydrologic analysis and ArcGIS to handle the data, and MATLAB for algorithms, Rivet and Excel for buildings and components. And there's some other tools that we have used, but it's like some tools in ArcGIS, so we need to use like HeckGeoHMS, ArcHydro, and some other tools to help us do the hydrologic analysis. I hope that I answered your question. Does anybody have any?
Yeah, yeah, yeah.
Go.
I got it. Thanks a lot. I have another query. I have actually two questions. One is that you're talking about Monte Carlo simulation at a community level. So, how do you take care of the computational demand that is there in your analysis? Do you account for any variance reduction or any kind of efficient uncertainty quantification methods so as to reduce your simulation time? And the next question
Yeah,
is
that's a
that
nice question.
about you talked about the building height, and you're talking about the resolution. So how do you get the building heights and this kind of data basically? So yeah.
Yeah, actually, so for this, the we used verse 100 simulation, but it turns out to give like not a smooth curve. So we ended up with 1000 Monte Carlo simulation, so we can have a very smooth curves like these curves. And the simulation for the 2D curves, it takes like half an hour or an hour to get results, but for the 3D curves, you have to wait for a few hours. So just actually, I didn't know any other ways to reduce the computational, the expensivity of the computational analysis. So it's very expensive for the 3D analysis because the for loop had to go through each component, which are 65, through each simulation, which is 1000 simulation, for each flood depth, which is like 1000 flood depths step and another 1000 flood depths duration, flood duration. So it takes like few hours actually to get done with one of these 3D curves. And actually, we are in the process of changing these fragility curves and decrease the damage states. So I have to run through all of these again and run all my simulation again based on the new damage states to get the fragility curves and surfaces. But this is how the best that we could do to develop the fragility curves and fragility surfaces. Did I answer your question?
Okay, thanks a lot. Yeah, yeah, yeah. That makes sense. Thank you.
Does anyone have any question?
Can I add something, please?
Yeah, sure. Go ahead.
Yeah, good evening, everyone, or good morning. I'm not sure about the times. This is Isra from Jordan. I'm an assistant professor in water environmental engineering in Jordan, Mota University. Thank you very much for this really interesting and neat seminar or webinar, and thanks to Azhar Razami for inviting me to attend such an interesting topic. It's actually really valuable work you've done and really interesting. I mean, it's flawless. You've done lots of things and bits of pieces. You put all everything together and presented really good results there. It's actually not a question, rather than it's a comment, because I've seen you've got a high resolution for flood risk analysis approach presented there, and you depended on lots of types of data, and it was probably available to you, because even the Google Earth is very high resolution, or I mean, it's, you can go in details to everything. How would you evaluate the possibility of doing such work in data scarce regions like, for
Yeah,
example, Jordan or the Middle East? Because
yeah,
I've got a project which talks about the, I mean, we're trying in that project to reconstruct a fatal flood that happened in Jordan, unfortunately, a couple of years ago, and we're stuck at the data level, even the very rough level of data. So how would you evaluate the possibility of doing such work? Is it like zero possibility, or we can do something and probably compromise on other things?
yeah, that's a good question. So for the let's divide the data. So we need data to do hazard map analysis, and we need data to model, to have high resolution model of the community, and we need data
Yeah,
to have high resolution vulnerability model for the community. So for the hazard analysis, so all what we need is we need high resolution digital elevation maps, and I'm pretty sure in the US, we were able to get LiDAR-based digital elevation maps, which is was resolution of 1 meter.
oh,
We currently are investigating the impact of the resolution of the digital elevation maps on the hazard simulation. So we are right now we are doing something is verification and validation model to check the impact of the resolution of the digital elevation map, and we have hazard maps from 1 meter resolution them and hazard map from 10 meter resolution them. So most all of the Middle East, I think they have from 10 meter up to 30 meter digital elevation map.
even 30.
We can do this.
Yeah, I think it's 30.
This is for the hazard. Uh,
Yeah,
let
actually, because
yeah,
for example, sometimes in the Middle East you find very narrow canyons.
yeah.
Uh, I think the sound is distorted there. So the canyon can be like few meters wide,
Can everybody mute
and
himself unless he's asking a question because there is some noise in the background? Yeah, I did it. All right,
oh, that's it.
go ahead.
So yeah, I was saying that the finest DEM resolution that we've got, I think, is the freely available DEM, the 30-meter resolution, and sometimes it doesn't actually represent the
Yeah,
narrow canyons, which are like less than few meters wide.
yeah,
So the whole canyon comes into one cell that's represented by one value,
yeah.
and that's the difficulty. I mean, we got stuck at the very early level of the project, so we started to manufacture some data, to be honest, or maybe use some drone photography or something like that to capture some effect of the DEM or the topography on the flood.
Yeah, actually, the DEM thing and the most all of the hydrologic and hydrodynamic analysis and the impact of these is more towards hydrologic. I'm not hydrologist actually. I'm just like grabbing
Right.
something from there and trying to work my way to get my risk. So I mainly focus on the exposure and the vulnerability. But based on what I saw and what we are doing, we currently and actually with 10 meter or 1 meter resolution them, sometimes there's many uncertainties and many factors that could affect your simulation. We in Lumberton we did a field study and we have high water mark for each building, and even with 1 meter resolution it gives a high variability in the
Yeah.
in the flood depths that we measured and the one is simulated. So, and we saw that there is like the boundary condition location affects this, the roughness that we choose affects this, and many things that could affect this. That's why we need to do calibration and validation for our model. We need to have at least 1 or 2 gauges in the study area or some high water marks and validate our work to match what happens in the field. So we still need some validation and verification model to verify the hazard model. But let me get you
Yeah.
to the exposure and vulnerability analysis. So for high resolution community model, right now or we will, in the next few months, we will investigate the impact of the data scarcity on the final loss and damage and other impacts on the community. Like, what if I don't have 15 building archetype and I assumed all the buildings within the community have one archetype? Like I merged, what if like I merged all these 15 building archetype in one, like and get the average loss and damage function for all of the 15. Or let's go up with the resolution and let's sum all the residential buildings in one archetype and say this is will be used to for the residential building, and this curve will be used for commercial building, and this curve will be used for service building or hospitals or schools. And we can go higher with the resolution. Let's sum all the one-story residential building in one archetype and all the two-story in one archetype. So we can investigate different resolution of building archetypes because we have 15. 15 and let's say, how did I know that the 15 is enough? No, it's not enough, but it's if you need more, you will have to develop more. So we can develop a different multifamily building, 3 stories, 4 stories, 5 stories to simulate all the buildings. So we try to come up with the minimum number of archetypes that enables us for now to make risk informed decision. So we can go up with the resolution with this 15 building archetype to make them 100, and we can go down to make them 3 or 1. This is for the community models, and see how this will impact the flood loss reduction and the damage of the buildings. And similarly, their fragility function. So if we use a one curve, if you use one archetype, so we will use one fragility or one damage curve. And if we use three, so we'll use 3 of them. So this is hasn't been investigated yet, but we can investigate it. And actually, this archetype is completely different from the one in the Middle East, in Egypt or Jordan. If we will go there, there is no wood building. Most of them are reinforced concrete buildings. So we need to develop archetype for the reinforced concrete with zero structural loss, because concrete will not get affected with the water that much, or if there is a foundation scour or something. So we need to look at the foundation. So that's my answer for now. So we need to actually go and dig on the impact of the resolution, not only on the flood loss and flood damage, but also their impact on the decision making. So how this will impact my decision in providing flood protection for the study area. So we need to look into this.
Exactly. It would be very interesting to have these, I mean, any published resources regarding that in the future, if you do this analysis.
What is that? Is that a question or?
I mean, it would be no. I mean, I'm just commenting. It would be really interesting to have. I mean, to
Yeah.
get in touch, keep in touch, so that we get some information of your future results regarding the impact of resolution
Yeah.
on the.
Because we are busy right now working on hurricane research on multiple test beds. So we will get back to the impact of the resolution. Actually, one of my colleagues studies this, but he studied this on the earthquakes and different types of data, but I will do it for flood in a different way.
Yeah.
Cool.
Thank you very much.
Thank you. Does anybody?
Uh,
Yeah, go ahead.
yeah, good evening, Khalid. Thank you for this very informative presentation. Let me just introduce myself. My name is Nasif. I've been working in the area of seismic mitigation previously in my doctoral research program at the Indian Institute of Technology, Delhi. But now I'm exploring this area of catastrophe modeling for multi-hazard scenario for building, including floods. And we also had two major floods in our area in Kerala in the last 4 years.
Where is that?
So one of the specific, we had two major floods in Kerala for
Where, where,
in the last 4 years.
where's this city?
Yeah, Kerala is a state in India. It's a
Oh,
state in India.
okay, gotcha.
Okay. Yeah. Yeah. So one of the specific questions that I wanted to ask you is, like, you have shown different damage states for structural and non-structural components in
Yeah.
your research. So how did you analyze them for which damage state they are in for a particular flood depth scenario? For example, you had shown the case of air conditioned place at a mean height of around 1 meter from the ground. So how did you determine in which damage state this component will be for a flood depth?
So
Is it
yeah,
a 1-0 scenario, or
No,
How does it
actually,
have an intermediate damage?
yeah,
Hmm.
the damage
Yeah,
states
please.
are based on the functionality of the building and how the essentiality of each component to provide the essential function for the building. So you can live in a building without a heater or without an AC. So it is not based on elevation. It is based on the essentiality of the building, the essentiality of the component to provide the 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 the, the main thing that you need in your home. You can live without AC if your AC is got flooded or your heater got flooded. You can live for a few days or few weeks until you get a new one. However, for other components like here, as you can see, we put the EC unit, the HVAC. I know it's a very small, but let's make it bigger.
Yeah,
Uh,
it's okay. It's okay. I think I
yeah.
can just see in
And
small.
then we move up to the damage states based on the essentiality of other components, like when you lose your appliances, such as your refrigerator, stove, washer, dryer. So you lose many things. So this is damage state two, which means that it's restricted occupancy. You cannot occupy the building without these main things. You have your cabinet damage, your washer and dryer. And similarly, damage state three when the water goes very up and hit your upper cabinet and damage all your counter components and valuable items in your building. So it is not based on elevation, it is based on the essentiality of the components to provide the main services to your building. It's something similar if you if something like tornadoes hit a city and the one of the power poles fall and you don't have a power in your city. You can live in your house, you can have a generator, you can live in your house without power, but the functionality was reduced. So it reduced by 10%. So it's something similar like this. And these damage states actually was decided based on a team. Like we have a Lumberton field study, and we go there and investigate. We actually have a lot of discussions about these damage states, and right now we have another discussion to reformulate these damage states to reduce them from five to two.
Okay.
Did you get it?
Okay. So if I understand it correctly,
Yeah.
what you're saying is that like you're treating like components, the non-structural components, as a single unit, right? So depending upon the flood depth, certain of the components will be seen as destroyed, damaged, completely damaged. For
Okay.
example, let's say that you have different components at different elevation which within the building.
Yeah.
So if let us say you have a flood scenario of say depth of 2 meter,
Okay.
and if your air conditioner is placed at 1 meter, then you are considering it to be completely damaged, right? It is in DS5,
Yeah, it's because it's a 2 meter and your AC unit is 1 meter, so it's damaged. Yeah. Uh, yeah.
completely damaged.
Yeah.
Okay,
And actually, we have
all right,
uncertainty. And
okay,
actually, if the EC unit at 1 meter and you have a flood depth of 1 meter, but we don't
hmm,
say that our EC unit at 1 meter, we have a 1,000 simulation that do a 1,000
right,
elevation of the EC unit. So
right,
at
right,
1 meter, you will have maybe 50% of your simulations are damaged and the other 50% are not damaged. That's why, because we don't know that all the buildings have the EC unit at the same elevation. That's why we need to have a
some kind
normal,
of variations, right,
yeah. And we
right,
didn't do it normal. We did a truncated normal distribution. We assumed an
truncated
upper
norm,
and lower
yes, yes,
bound because we can't imagine that the EC unit we will dig in the ground and have the EC unit under the ground. So we need to
right,
truncate the normal distribution at the ground elevation. Similarly,
right, right.
other components. Yeah.
Okay, so essentially, like when the flood depth touches the depth of the air conditioner, it is treated as completely failed for the air conditioner, right?
Yeah.
Like I'm what I'm trying to do is I'm just trying to compare it with like when we do it in seismic, when we consider seismic effects, we define the damage states depending on
The
the drift
structural
in the
damage.
building. For example, if you're yeah, if you're saying if it is within some particular drift, then this is a damage,
Yeah, I
right?
know. Yeah.
So I was wondering, yeah, if there
That's
is some kind
completely
of analysis
different
which
from
we actually
flooding. Yeah, each hazard has its own nature,
approach.
and most all of the main thing that makes flood unique hazard is that it has more content damage than a structural damage for riverine flooding or
Right.
for static flooding.
Right.
I'm talking differently from
Right.
the flooding from surge and wave. So we
Okay.
care more about content because the structure will be safe, but the content will be lost. And the content also
Right.
is essential for the occupability of the building.
All right. Okay. So just one more question, and I'll just conclude.
Go ahead.
Yeah, you said in the in the beginning that you had considered three maps. One is the elevation, the other shows the occupancy, and you also had used a soil map, right?
Oh,
So what we have observed, like in the last few floods here, is that in some buildings there is a lot of scoring that happens at the foundation level, due to which the building gets damaged.
yeah.
So, have you considered soil for any other reason in the current research?
Yeah. So let me make it clear. So when I say soil here, it's the nature of the soil and the study area, like the whole soil of the study area, like because the soils are the different soils are different in their permeability. So this affects the amount of
Right.
water surface runoff. And actually similarly the land use. If you have
Okay.
a forest area and you have a paved area like a road that has pavement or a concrete pavement, so the permeability of the land use that has forest is more than a road that is paved. So we will have more water surface runoff on
Hmm.
the pavement area. So that's why that's needed for the hazard map. But if we are talking about the soil underneath a building that is saturated and cause some scour, so we need to start with the building that it has not 100% or like the flooding get to the building that is already damaged or that is already have some structural damage. So there's some loss. So you start with initial loss of the building before the flooding. Like the building is worth 90% because 10% of the building is already lost because it has some scour in it. So that's why we
Right.
collected the current maintenance of the building. So we have it. Like we give it
Okay.
poor maintenance,
All right.
medium, or high maintained, or well maintained.
Okay. All right. Okay. Okay.
All right.
Thank you very much,
Thank you.
Khalid.
Yeah. Does anybody have any other question? All right. So I'm happy that you guys were able to join. I know there was like 21 registered on the Zoom link, but I shared it live. So it's supposed like many people were able to saw it live on LinkedIn and YouTube and my Facebook. So I will go back and see if they have any comments or any questions on YouTube or my Facebook. Yeah, happy to have you all and have a good night or have a good morning, whatever the time you are in. And let me know if you have any other question, just email me or send me a message on LinkedIn. Have a good one. Bye, guys.
Okay. Thank you so much. Good day to you. Bye bye.
Thank you.